Welcome to Mr. Frolic's physics classes. In this lecture, we're going to learn about precision and accuracy.
Hi there. Before we actually get into precision and accuracy, the first thing we need to see is the idea of random error and systematic error. So random error is the error that is natural part of your experiment. So random error will always happen. Okay, random error always happens, and it is part of the process of measuring, is part of that uncertainty. A good experimenter, good experiment would have low random error. And a sloppy experiment will produce high random error. Systematic error, on the other side, it's not necessarily something that will be happening in every single experiment. Actually, quite the contrary. It's due to some, usually, a problem with your equipment, okay, or a systematic mistake made by the experimenter. So this one here is going to be caused by non-adjusted equipment. So the slide here shows us the idea of a meter stick where the zero has been worn off. Okay, this is a slide, a picture from Tim Lund, who I got from my AB times, and he allows us to use those. Thank you, Tim. But in there, the zero is a bit worn off. So every measurement made with that meter stick will be off by the very same amount. And that's the idea of the systematic error. You could produce a systematic error because you forgot to zero the scale of your balance. So a balance, the zero offset on the balance, or on a voltmeter, for example. Okay, and so all results will be skewed by the same amount. Now, this can also be caused by a mistake on experiment. For example, you are supposed to have drawn, put your beaker and discounted the mass of the beaker, and you forgot. As you're measuring the length of a pendulum or of a string, you should have added the mass of the hook, and you forgot. Something like that. Okay? On a graph, this is what we see. Let's say that this is my expected result. Okay? And your group gets this here, these data points. We can see that my results are very close to my data where the spread is small. So this here would be a graph with low random error. Now let's say that another group running the same experiment gets these results here. Gets these here. Again, this is my expected result. And these are my data points. And you see lots of variation. So this would be a high random error situation. Now, systematic error. Let's see a couple possibilities. Let's say that this is my expected result, and because of a zero offset mistake, like you forgot to zero the scale, or the meter stick was worn off, something, you could, for example, skew all of your data like this. So you get another line that is maybe has the same slope as the expected one, but is shifted up. And this shift is exactly caused by systematic error. Or maybe, you know, depending on the kind of mistake you made, you still kind of get roughly the same generic line. Let me just repeat this graph in here so it's easier to visualize. This is my expected result, but because of a mistake in calibration, perhaps as you were setting the scale on a video lecture, you did not set the scale properly. And even though you kind of start roughly at the same spot, but your line is completely off this way. So this would also be caused by systematic error, most likely. Now let's talk about precision and accuracy. So precision has to do with how exact Now let's talk about precision and accuracy. Precision has to do with how exact a measurement is. The more decimal places you have in a reading, more precise you are. Basically, that's the idea. Accuracy has to do with close to, and put this into parentheses, quotation marks, correct value. So something is accurate if it is close to the exact value. Let's give an example. Let's say that Bob steps on a scale. Okay, so here's Bob. And that Bob's body mass is 60 kilograms. So the actual result is 60 kilograms. But the scale reads 71.962 kilograms. This scale is precise, but inaccurate. I hope I'm spelling this right. Okay, so it's precise but inaccurate. It's not close to target value, although it has several digits in there. Another reading for example, $60.5 kilograms. This reading now is maybe not that precise, but relatively accurate. Okay? So basically, that's the idea of precision and accuracy. In a lab, in a lab, usually a precise measurement, precise lab will So repeated results, repeated measurements will produce similar results in a lab. Okay? And the idea of accuracy on a lab is your result comes close to expected value. So you're measuring the acceleration due to gravity, and you expect to be 9.8 meters per second squared, and the result is close, 9.9 meters per second squared, 10 meters per second squared, then your result will be accurate. When we connect this now to our idea of errors, precision is related to random error. Usually, something very precise will have an experiment that is very precise will produce small random error. An experiment that is not precise is related to large random error, caused by large random error. And accuracy is related to systematic error. So if you have a small systematic error, you are most likely going to be accurate. And if you have a large systematic error, you most likely will be non-accurate. Well, perhaps the best example to visualize precision and accuracy is the idea of someone on a shooting range and aiming at a target. So I'm posting now here another part of Tim's slides, possibilities of shooting range. So the first one, the shooter is not good, which means that when the shooter aims, he does not hold still. So as he shoots, his impacts will fall on several different spots. They are spread out, large random error. And the sight of his gun is out of alignment. So he aims here, but the impacts are down here. That is a systematic error, and you can see then that his results are off-center. On the second example, the gun is properly aligned, but he is a poor shooter. So his results are completely spread out, although on average he hits bullseye. Don't know how useful that is, because if you're shooting at something that is coming to attack you, and then you hit 1 meter to the left of the target, then 1 meter to the right of the target, you on average hit 2 impacts on the center of mass. But, well, I don't think it's going to stop him. This here is the second result, shows high random error, although a small systematic error. The third situation here is a good shooter, so he's holding his gun steady. He shoots always on the same spot, but his gun is out of alignment, meaning again that he shoots here, but the impacts happen down here. This situation is precise but not accurate. In terms of error, relates to small random error but high systematic error. Now, the last one is the ideal world, is precise and accurate, because the impacts are always on the same spot and the gun is aligned. So he's always hitting very close to the target value. This is small random error plus small systematic error.